Welcome to NASA headquarters in Washington, D.C. I'm Steve Cole from the Office of Communications. NASA is getting ready to launch its first Earth science satellite in 2 years, dedicated to tackling some of the toughest questions about our Earth's changing climate. The mission is Glory, and it will join a fleet of NASA satellites already in orbit circling the globe every day. Glory is scheduled to rocket into space early in the morning of February 23rd from Vandenberg Air Force Base in Southern California, on its way to an eventual orbit of nearly 440 miles above the Earth. Today, we're giving you a preview of this mission with some of the key people who have made Glory possible. Let me introduce you to our panelists. Joy Bredhauer from NASA headquarters is the Glory Program Executive. Brian Faithful from NASA's Goddard Space Flight Center in Greenbelt, Maryland, is Glory Project Manager. Michael Mischenko from NASA's Goddard Institute for Space Studies in New York is the Glory Project Scientist. Greg Kopp from the University of Colorado's Laboratory for Atmospheric and Space Physics in Boulder is the Instrument Scientist for the Total Irradiance Monitor. And finally, Brian Cairns, also from NASA's Goddard Institute for Space Studies, is the Instrument Scientist for the Aerosol Polarimetry Sensor. After our panel's presentations, we'll take questions here in the auditorium and on the phone line from the media. So let's get started. Our first speaker, Joy.
Now I'll talk about why Glory is important to us. May I have the first graphic, please? Glory is the next launch in the President's Climate Initiative to address key climate problems and is NASA's next Earth-observing research mission that will join 14 other satellites. Glory will improve our understanding of how the sun and tiny airborne particles called aerosols affect the Earth's climate changes. As the Glory Program Executive for the Earth Science Division, I am responsible for the overall technical, cost, schedule, and program management of the Glory mission for NASA headquarters. NASA's rigorous practices, standards, and processes have prepared us to launch the observatory and the launch vehicle. Project management for the Glory mission is provided by the Goddard Space Flight Center, where Brian Faithful is the project manager and Michael Mischenko is the project scientist. The Taurus XL launch vehicle, which was procured through the NASA Launch Services Program at Kennedy Space Center, will launch the Glory Observatory, which will then ascend into the A-Train, or the afternoon constellation. The low Earth orbit A-Train consists of multiple spacecraft flying in close proximity to create basically the first ever super observatory that will give us near simultaneous observations of the Earth, including land, ocean, and atmosphere. The highly accurate and precise data from Glory, in combination with observations from the rest of the A-Train, will enable researchers to improve our understanding of the Earth system by improving our ability to predict future climate. I'd like the next graphic, please. The Glory mission will assist researchers in revealing the effects of aerosols and solar radiance on climate. Changes in the composition of the Earth's atmosphere or in the total solar irradiance can lead to global climate change. The knowledge obtained from the Glory mission will help us better predict the future of our planet. The Glory mission responds to the Intergovernmental Panel on Climate Change by continuing and improving on NASA's Earth science research on future climate. The scientific knowledge provided by the Glory mission is essential to improving climate models that predict future climate change. This understanding is also essential for making scientifically based economic, health, and policy decisions related to environmental change. The Glory mission has two science objectives. The first objective is to continue our 32-year record of measuring the sun's direct and indirect effects on climate. The second objective is to increase our understanding of how natural and man-made aerosols affect Earth's climate changes. The Glory mission will address the largest uncertainty in our understanding of the Earth system. Basically, the aerosol climate effect. We'd like to better understand how aerosols influence solar energy in the Earth system. There are uncertainties in how the solar energy influences, there are uncertainties in how aerosols contribute to basically the absorption and reflection of solar energy, as well as in how aerosols impact cloud formation and properties. I'd like the next graphic. Thank you. Aerosols are tiny airborne, solid or liquid particles that are sized from nanometers to micrometers that may be either natural or man-made in origin. And they come from sources like this graphic, desert dust. The next graphic, please. Volcanoes. The next graphic, and air pollution that contribute to either the warming or the cooling of the Earth. Man-made aerosols are created by burning either fossil fuels or intentionally burning trees, and they contribute to the warming of the Earth. While sulfates, which are also created by burning fossil fuels, can come from sources like volcanoes and air pollution, contribute to the cooling of the Earth. I'd like to show the next animation. This animation is a model, basically, of aerosol transport. Glory will help us to improve atmospheric models that predict aerosol transport. This model is an atmospheric model demonstrating the eruption of Mount Pinatubo. This is not obviously Glory's data, but an example of a model that Glory can contribute to. Now, unlike greenhouse gases, which can remain in the atmosphere for years, these tiny particles remain airborne for at most a couple of weeks, during which time they can be transported globally thousands of miles. Glory is NASA's first satellite that will make unique, highly accurate measurements of light properties as a means of identifying the size, shape, and composition of aerosols. These first ever measurements from Glory's aerosol polarimetry sensor instrument will help in determining the global distribution of both natural and man-made aerosols, as well as how aerosols interact with other components in the atmosphere as they are transported globally and affect climate change. Brian Cairns will address the aerosol science for the Glory mission later. And I'd like the final graphic. Thank you. Glory's other science objective is to understand how changes in the sun's energy can cause climate change. Our sun provides the energy that fuels Earth's climate. It's the most dominant factor driving the climate. The highly accurate measurements from Glory's total irradiance monitor will help us to understand the sun's major effect on Earth's climate with improved accuracy and stability, and will also help to continue more than 32 years of critical solar irradiance data. Gray Kopp will address the total irradiance science for the Glory mission at a later time. And in summary, the Glory mission will provide the highly accurate aerosol and solar irradiance data measurements that are vital to improving climate models and more accurately predicting the Earth's future climate. Additionally, this will serve as a resource for making scientifically based economic, health, and policy decisions related to environmental change. And now, I'd like to turn it over to Brian Faithful, who will talk about the Glory Observatory, and as well as the launch site activities for our upcoming launch.
Thank you, Joy. I'd like to thank everybody for being here today and tell you how excited we are to be at this point in the program. Can I have the first graphic? I'm happy to report that the observatory arrived safely at Vandenberg on Tuesday, January the 11th. We have successfully completed all post-shipment inspections and functional tests. Can I have the next graphic? And the engineering team is currently preparing the satellite to start fueling this weekend. After that, we will be ready for fairing installation early February. Next graphic. In early February, excuse me. In addition to the observatory work, the Taurus rocket is making significant progress as well. And in fact, on this past Monday, they erected the first stage at the launch site, which you're seeing on the picture now. If we could start the animation, I'd like to talk a little bit more about the mission. As was previously mentioned by Joy, Glory is a key part of NASA's climate research program, and it will fly in the afternoon constellation with several other Earth-observing satellites. It is a unique satellite, and it's really two scientific missions in one. It contains a sun-pointing instrument that measures solar energy and an Earth-pointing instrument that will study aerosols. The Total Irradiance Monitor, built by the University of Colorado's Laboratory for Atmospheric and Space Physics in Boulder, Colorado, will continue a 32-year spaceborne data record of the total solar irradiance measurement, while the aerosol polarimetry sensor that was built by Raytheon's Space and Airborne Systems in El Segundo, California, will help scientists better understand the effect of both man-made and naturally occurring aerosols in the atmosphere. The APS instrument is supported by 2 cloud cameras, which were built by Ball Aerospace and Technologies Corporation, and they are used to assist in cloud clearing for the aerosol retrievals. I must say that all the instruments on Glory have outstanding performance and have performed flawlessly throughout the long environmental program that we've had. Could we start the spacecraft video? Glory used an existing spacecraft bus that was available from a program that didn't fly. And in order to accommodate Glory's 2 scientific instruments, extensive modifications and in general reconfiguration of the bus was required. This very challenging transformation was successfully performed by Orbital Sciences Corporation in Dulles, Virginia. And I'm glad to say that it meets all its performance requirements. Could I have the next graphic? Before I hand this off to Michael to talk more about Glory science, I want to express how happy the team is and excited to be here and to let you know that the Glory Observatory is ready to launch and do its mission. Michael?
Thank you, Brian. My first graphic will tell you that essentially all of the energy that fuels the climate system comes directly from the sun. This means that even small changes in the solar energy input can have profound consequences for the Earth's climate. This means that we have to measure the solar energy input over an extended period of time with a very high accuracy, and this is precisely what the Glory team is going to do. It will continue the 32-year uninterrupted record of total solar irradiance measurements from space. In fact, this instrument is significantly more accurate than all his predecessors and will help us to improve the overall accuracy of the existing composite record of satellite measurements. Once the solar energy enters the climate system, it can be partially absorbed at the surface or in the atmosphere and can be partially reflected back to space. In fact, it is this delicate balance between the incoming solar radiation and the outgoing radiation that defines the Earth's climate. An extremely important role in this redistribution of the solar energy in the atmosphere is played by tiny yet ubiquitous particles, airborne particles called aerosols. These particles can affect the climate directly by absorbing or reflecting light. So depending on their chemical composition, they can contribute to warming or to the cooling of the atmosphere. They can also affect climate indirectly by modifying the properties of clouds, which are significant reflectors, you can see from this picture, and modulating precipitation. So this tells us that because of this important role the aerosols play in the redistribution of the energy in the climate system, we need to know their distribution, global distribution, and properties with very high accuracy. And this is the major scientific objective of the Glory aerosol polarimetry sensor. The next graphic is a computer simulation. It was created using a theoretical computer model and shows you the transport of tiny soot or black carbon particles in the atmosphere. So we have these theoretical modeling tools, but we still know that the accuracy of these tools is insufficient and needs to be improved. We know that the aerosols affect climates. The effect on climate by aerosols is comparable in magnitude to that of the greenhouse gases, yet the existing uncertainty in the climate forcing due to aerosols is as big as the estimated forcing itself. Also, if you look at the anthropogenic or man-made contribution to the global climate change, there is an uncertainty in that, and it's a significant uncertainty, and almost all of it comes from the poor knowledge of aerosol particles. So this all tells us we need to know these particles much better than we do, but it's not easy to do. There are several factors which make this problem quite complicated. The aerosols come in all sizes, shapes, and chemical compositions. There are different types of aerosols which can coexist within the field of view of a satellite instrument, making the problem of the determination of the aerosol properties highly complicated. These particles are short-lived and highly variable, yet they can be transported thousands of kilometers and even over the globe. These complexifying factors call for a very special instrument to study aerosols, and in fact, the Glory aerosol polarimeter sensor is the first Earth-orbiting instrument of its kind. It will measure not just the intensity of the reflected sunlight, but it will also measure the polarization state of this light, and it will do that with very high accuracy. It will measure the reflected intensity and polarization for a seen location from 250 different angles in 9 spectral bands covering a wide spectral range. So APS will provide a wealth of information for each scene location, and this wealth of information is precisely what will help us to determine the properties of aerosols with the requisite accuracy and specificity. The next graphic tells you that the Glory spacecraft will be flown in the so-called afternoon constellation of satellites. For the team instrument, it doesn't matter how we fly it, because all it does is to look at the sun and measure its energy output. But for the Glory APS, flying in the A-train can be quite beneficial, because there are multiple other instruments looking at the same scene location at about the same moment in time. And by combining these measurements, we can come up with a product that is better than the product of each of the individual instruments. I'll give you just one example. Glory will fly right behind the Calypso spacecraft carrying a LiDAR. The LiDAR measurements are very sensitive to the vertical location of the aerosol particles, but are relatively insensitive to the particle properties. With the Glory polarization measurements, we have extreme sensitivity to the particle microphysical properties and little sensitivity to the vertical position. So by combining these two types of measurements, we will, for the first time, determine the vertical distribution of aerosol physical properties. This has not been done before. And now Greg Kopp will tell you more about the team science.
Thank you, Michael. The total irradiance monitor on Glory is looking at the sun, and as Michael said, the sun is providing nearly all the energy input that drives the Earth's climate system. The sun provides 10,000 times more energy than the next dominant source, 4,000 times as much energy to the Earth's climate system as all the other sources combined. And that energy from the sun, incident at the top of the Earth's atmosphere, varies with time, as you can see in this first animation. The blue line in this animation gives you the TSI, total solar irradiance, the energy, radiant energy from the sun at the top of the Earth's atmosphere driving our climate system, and you can see that it varies. Solar activity, such as the passage of these dark sunspots across the solar disk, cause short-term decreases in the sun's output. These are decreases on the order of 0.1 to 0.3%, and they can occur rapidly over days to weeks, as you're seeing here. This animation spans about 3 months of the sun's output. These short-term fluctuations, although large, have very little effect on Earth's climate because the climate system doesn't respond very quickly to changes in the sun's output. But knowing that the sun can respond and change this quickly, we'd like to know long-term how the sun changes over decades, over centuries, things that can be much more relevant to climate change on the Earth. And being able to measure something such as these small-scale changes on the sun over decades to centuries drives real stringent accuracy and stability requirements, which we're going to be achieving with the TIM instrument on Glory. The next animation shows the 32-year-long record that scientists currently have from space of total solar irradiance measurements. The different colors on here represent measurements from different instruments. And you'll see that they're each following the same sort of curve, the same output that the sun has, the same variability that it has. But you'll also see that there are offsets between each of these different instruments, and those are due to calibration differences. What's helped this record has been that we've had overlap between each of these different instruments. Each instrument has taken simultaneous measurements of the same sun at the same time as prior instruments. And that's what's let us overcome these offsets to be able to, as the next animation or the next slide shows, to be able to offset these different measurements to form one continual record of what the sun has been doing. We use that then to determine sensitivity of the Earth's climate system to solar output. But we need to continue this record. We need this overlap with prior measurements still. And so Glory, as shown in the next animation, will be following on to the total irradiance monitor that's currently flying on NASA's SOURCE mission, and the total irradiance monitor on that spacecraft mission. Glory will be continuing that record to make sure that we don't have any interruptions in this data set. So with this long ongoing record, as shown 2 slides back, we're going to be continuing this measurement record to take care of these offsets. Glory also is going to have improved accuracy, which will make the future record less susceptible to gaps in the data, because we'll know with very good absolute accuracy what the value of total solar irradiance is right now. By extending this record, as shown in the next view graph, by continuing this record, we'll be able to determine what the total solar irradiance value truly is. We'll be able to determine what solar features are causing the variability that we're seeing in TSI. We'll want to be looking at long-term, decadal, century-level timescales. One slide prior to this, please. Decadal and century-level timescales, what kind of long-term variability we're seeing from the sun, and ultimately we're going to be determining what the Earth's sensitivity to these solar fluctuations is. So this is going to be giving us a very accurate measurement of the incoming radiation, and next Brian will be telling you a little bit about how Glory is going to be tracking that radiation as it's scattered or reflected by aerosols in the Earth's atmosphere.
Thank you, Greg. As you've heard, the aerosol polarimetry sensor is designed to detect and characterize particles in the air, all the way from small smoke particles and pollution that are smaller than a human hair, all the way up to very large particles, such as those in ice clouds. Can you show the first image, please? This just shows that you can go from the very small particles to the very big particles very quickly. On the left side is pollution flowing out of Mexico City across the high plains and coming up against a cloud in the coastal range, and the volcano in the middle is the Pico de Orizaba. This image was taken during a field campaign, the NASA INTEX-B field experiment, and we flew our airborne simulator of the APS during this experiment. What the polarization measurements that we take allow us to do is to detect and characterize the aerosols over the bright high plane in a way that is not possible with measurements just of intensity. And if you're looking at a nice fluffy cloud like the one in this image, the best way to figure out what the size of the drops in that cloud is to look at the polarization. Could you show the next image, please? Typically, when we're walking around on the ground and you look up at a cloud, you don't normally see the rainbow. This is for 2 reasons. One is the geometry is often not right, and the other thing is the cloud is bright, and the sheer brightness of the cloud doesn't allow you to see the rainbow. These 2 images are taken of clouds, the same cloud a few seconds apart, and on the left, a polarizer is used so that you can see the rainbow, and on the right, there is no polarizer used, and the rainbow is no longer visible. What we can use the rainbow for is to determine the size of the droplets in a cloud with exquisite accuracy. So you can determine how big those droplets are to within 1/10 of a micron, and you can determine the width of the size distribution as well. Next view graph, please. As we've discussed, aerosols are one of the things that can change the climate. Here you can see that the aerosols obviously scattering light over Los Angeles, and so they can scatter light back out to space, cooling the Earth. They can absorb light within the atmosphere, and that can warm the atmosphere and change its stability. So they can have 2 effects. One is on the thermal state of the Earth, like cooling or warming it, and the other is on changing the water cycle by changing the amount of evaporation at the surface. Not only can aerosols have those kind of effects on the climate of the Earth. Next view graph, please. But they can also modify clouds, and this is a cartoon just showing one of the possible effects that these little particles can have. Every single droplet or ice particle in a cloud is formed on a small dirt particle initially. And depending on how many of those little particles you have, how big they are, and what they're made out of, determines how many droplets you get. And this is just showing that if you take the same amount of water and split it amongst multiple droplets as opposed to having a fewer number of droplets, you can make your clouds a lot brighter. And obviously this can have a huge effect on how much light gets to the surface of the Earth. And this is the reason why we not only want to detect and characterize the aerosols, but also to determine the size distribution of the droplets in clouds and also ice particles. So in summary, the APS is designed to detect and characterize both aerosols and clouds and improve our understanding of aerosols and clouds and their effects on climate. Back to you, Steve.
Okay, thank you, and thank you to all the panelists. We'll first take questions here in the auditorium from any media and then go to the phone lines if there are any questions at this point. Actually, before we go to the phone lines, let me just ask one question that I had. You mentioned that NASA has many satellites up there, Earth observing satellites, 14, I think you said. How does Glory fit in the cost range of all those missions? I'm sure we have some big ones, some small ones. How does Glory fit into that range?
Of the 16 missions that are currently in NASA's portfolio, in our science portfolio, the Glory mission compares pretty well near the bottom range of cost in that existing scale of missions that we have right now.
Okay, thank you, Joy. Again, any questions here from the media? I guess we're getting one question.
Hi. Could you tell me how long will Glory be measuring the atmosphere?
I can answer that. Glory's designed for a 3-year mission lifetime, and we're sized for 5 years with consumables.
After that, then what happens?
That we have to.
After that, we'd have a review that would then determine when and how long the Glory mission would go into what's called extended operations. So that would have to be another gate or approval in the process after the baseline mission is completed.
So in other words, if this works for you guys, then you'll do a continuation with another rocket or satellite.
Yeah, that decision would be determined based upon, I guess, the performance of Glory as well as the other missions that are in the pipeline right now.
Okay, thank you.
If the satellite's still working, the satellites beg to keep taking measurements.
They never want to turn off.
Okay, we don't have any media questions on the phone line, so I'll throw out one more and give the media and the audience a chance to ask one more. Distinguishing the sources of aerosols based on the different types of aerosols seems to be a key question for Glory. Could somebody speak to how well we understand the percentage of aerosols coming from different sources now, and how will that improve, that estimate of what's coming from what sources, volcanoes, desert dust, into the future with Glory data?
Maybe I'll answer. At this point, the only estimates of how much of the aerosols are natural and how much are man-made, these estimates come from models. Because satellite instruments that have been in operation so far, they simply cannot discriminate between natural and man-made particles. The only way to do that indirectly is to determine the refractive index of the aerosol particles, and this is where polarization is especially powerful, because the polarization state of the reflected light is very sensitive to the particle refractive index, which is a proxy to the chemical composition. So in this respect, the Glory APS will start a new record of satellite determinations of the particle refractive index and chemical composition. From the models, I think the models range quite a bit in estimating the percentage of the particles that are natural and man-made. There's a whole range of estimates, and I don't think there is a consensus.
All right, thank you. We do have a phone question from Nora Wallace at the Santa Barbara News Press. Please go ahead, Nora. Nora, are you there? We're not hearing any question from Santa Barbara. Okay, we have a second question. We'll go to James Dean at Florida Today. We're still not hearing any question, but let's see. If there's any other, no, we're not getting that question from Florida Today either. Well, once again, around the, if there's no more questions in the media from the audience, we'll wrap up the briefing. I wanted to say that if you're interested in getting more information on the Glory mission, please go to our website, and that is www.nasa.gov/glory. And thank you all for watching today. Goodbye.